Hi, welcome to the glass plate. In one of the lectures concerning drag force, we discussed a paratrooper coming down, but we didn't discuss what its velocity is. So let's, in this example, try and do it. First I'm going to draw the chute, and then somebody is hanging at the chute, coming down with velocity v, terminal velocity that we would like to compute. For this we need to consider the forces, and obviously as gravity is one of the forces that I first draw in, we also need the mass m, which is about 100 kilogram for an ordinary male person, including the chute, which does weigh as well. Okay, that is force number one. There are other forces acting on it. There is a small buoyancy that I draw, and there is a large drag coming from the chute basically. And we know for the terminal velocity we can find it by equating these forces, buoyancy and drag, upwards, gravity downwards, all three to 0. They will give the terminal velocity. In this example I'll ignore buoyancy. It's pretty small compared to gravity. So basically drag and gravity are in equilibrium. The drag force, as we know, is CD, A perpendicular, half rho of the air, V of the paratrooper and chute squared, and gravity, which I have to subtract, is minus mg, and this is 0. V is the one that we need to know. Density of air is 1.2 kilogram per cube. G we know, 9.8 meters per second square. The A is coming from the chute. It is the frontal area of the chute, which is basically, if you look at the frontal area from the air perspective, a circle with diameter big D. So the frontal area is quarter pi d squared, d on the order, well, let me write it here, on the order of 10 meter. CD is for the time being thus an unknown, and we know that we need to look it up. We could do that, and we immediately realize that probably this is a terminal velocity at high Reynolds number. The reason is that V may not be too big, but the D in the Reynolds number is big. So I anticipate that the Reynolds number is high. And then I look up for such a shape what the CD curve is. And the value is 1.4 roughly. Now I can equate V. So if I do that, I have V on the one hand is the square root out of mg, a 2 from the half. I need to divide by pi over 4 g squared for the area, the rho of the air, and the CD coefficient. The right hand side is completely known, and I can fill in my numbers, and I will back out that this is roughly 4 meters a second. So we answered the question, what is V? 4 meters a second terminal velocity coming down. Now we could think about what does it mean? How hard does the trooper hit the ground? And to do so, we could do just a simple estimate. Suppose that the same person would jump, so here's the same person, from a table, and the table has a height, or a building, I don't know yet, has a height h. With what velocity do you come down, or rephrased, 4 meters per second, which height? For this I can equate basic kinetic energy with which you come down is coming from the potential energy mgh. And thus the h corresponding to this 4 meters per second is v squared over 2g. V squared 16, 2g, roughly 16, so this is on the order of a meter. Not too bad. Anybody can jump from a table, and with a little luck you'll end straight on your feet on the floor. This is an example of how you do these type of exercises. Try them yourself. Good luck.